Hey there, it's Jamie. I realized today during lecture that I kind of botched the explanation of joint and conditional probabilities and showing you how to calculate it. So I'm going to do a quick video so that you can see it in a little more succinct and clear way, and I hope this makes a little bit more sense. So you can see my screen, I am hoping, and what we're going to do is start with that data that we downloaded today. You can get this in Module 2, Chapter 5 Resources. It's the lecture data. And what it is information on 300 customers. I know it's 300 because I can scroll down to the bottom and see that there are 300 customers. And these are customers of a bank. This is fictitious data. And we've got a few variables on them in this data set. We've got age, marital status, annual income, the amount of their mortgage, the number of payments they make per year, the total amount of their mortgage they've paid off, and whether or not they've defaulted on their mortgage. And so we're going to use this data to explore a couple of questions. First, what's the probability that someone's going to default on their mortgage? And we would write that as probability of D. And then we're going to also explore this by marital status and wonder if someone's marital status influences the probability that they'll default on their loan. The probability of default given that they're married, or the probability of default given that they're single. So that's how we would write that. So I'm going to start here by taking this data and summarizing it into a pivot table. So to do that, I take my cursor and I click on any cell within the data set, and then I choose Insert, Pivot Table, and when it asks me where I want it, you'll just put new worksheet, but I'm going to put it someplace because I've written some formulas and I want to save those. So I'm going to put it in an existing worksheet that's called Pivot Video, because that's what I'm doing right now. And I'm going to put it there in A1. And here I get my option to make a pivot table. So what I'm going to do is summarize this table to look at how many people I have, and then I'm going to create a table of counts that separates by marital status and default status. So I'm going to put marital status in the row. In the column, I'm going to put whether or not they defaulted on their mortgage. And then I'm going to drag down defaulted on their mortgage and put it in values. And here we go. We've got a great table. I've got married and single in the rows, and I've got default, no, and yes in the columns. I'm going to reorder this because it makes more sense to me if I have yes first. Then in the grand total, I've got 143 people that are married, 157 people are single. You can see that that adds up to 300. I've got 120 people that defaulted on their loans and 180 that did not. Those two numbers taken together add up to 300. Also in these counts, of those 143 married people, 79 defaulted on their loan and 64 did not. Those two numbers taken together add up to 143. And of single people, 41 defaulted on their loan and 116 did not. Taken together, those add up to 157. So when we have historical data like this, when we're thinking about probabilities, what we're really going to be calculating is the percentage of people that fall into each category. So to make it easier to work with and make it easier for you to follow my formulas, I'm going to remove this pivot table but keep the information. So I'm just going to highlight it, right-click and choose Copy. Then right on top of itself, I'm going to attempt to paste Special. Let's see if it works. It worked earlier. Okay, I'm going to paste it down here. I'm going to paste the values. Then pardon me while I tidy this up a bit. I'm going to just delete those first few rows, and I'm going to have to expand my table, or this is my little formulas, and then I'm going to have to drag my equations around. Don't mind me. Great. We'll get to these in just a second. All right. Now, this is my information from my pivot table, but it looks a little bit different. So I've got married people here, and I've got single people here. I've got non-defaulters. I've got defaulters, and I've got non-defaulters. I'm just going to center all this, and I'm going to change the font because it's going to make me happy. You don't have to do that, but here we go. Okay, so here's my population, 300 people total. Let's calculate a few probabilities. So I'm just going to start off by calling this probabilities. And then I'm going to go below and I'm going to calculate some joint probabilities. Actually, I'm not going to type that in yet. We'll do that in a second. And then I'll do conditional probabilities. So let's take a couple of probabilities. Let's take the probability that someone's married. Let's take the probability that someone's single. We can calculate both of those. We can also calculate the problem that someone defaults. I'm going to call that probability of D. And then the probability of that they don't default, I'm just going to call that the probability of the complement of D, using that apostrophe to indicate the complement. The textbook uses a superscript C, but I can't do that in a cell in Excel, so I'm going to use the D apostrophe. So to figure out the probability of being male in historical data, that's the same as asking what percentage of our sample is male. And so I'm just going to take a look at married. I've got 143 married people out of a full sample size of 300. So the percentage of people in my sample that are married is going to be 47.6, or a probability of 0.477. We can think of this that if we were to select one person at random from that sample of data, there's a 47.7% chance that that person would be married. Let's do the same thing for single people. I take the number of single people here, 157, and I divide it by 300. And I can see that the probability of selecting someone at random from that sample who is single is going to be about 0.523 or 52.3%. I'm going to give you some formulas. So we can do the same thing for defaulting and not defaulting. So we have 120 people that defaulted on their loans out of 300. And so as a ratio, that's 120 over 300, or 40%, 0.4. If we were to choose someone at random from that sample, there'd be a 0.4 probability, or a 40% chance that they defaulted on their mortgage. For those who have not defaulted, it's 180 out of 300, otherwise known as 0.6 or 60%. If we take a look at married or single, these are mutually exclusive events. You can't both be married and be single. Similarly with defaulting, they're mutually exclusive. You either did or didn't. So those are mutually exclusive. These totals for these mutually exclusive events, if you add them up, will add up to 1. So here are our probabilities based on historic data. Now let's look at something else, which is joint probabilities. Let's look at the proportion of our sample that fits into these overlapping categories, right? The intersection of married and defaulted, or the intersection of married and no default. What proportion of the population fits into those categories? In other words, what's the probability that someone chosen at random is going to be both married and defaulted, or both married and not defaulted? We can calculate 4, one for each of those inner categories. So I'm going to put right down here, I'm going to skip a row, and I'm going to call this the probability of married and default. And then I'll look at the probability of married and default prime. So the real notation for this isn't an and sign, but I can't do that upside down U. Normally it would look here, like in this second equation, the probability of that someone both defaults and they're married. That's the same thing as saying married and defaulted, because it's that overlapping, that intersection. And then we've got 2 more. We've got the probability that you're single and default, and the probability that you're single and default prime, that you're current on your mortgage. So let's do all of those. Same idea here. In the married and default status box, we've got 79 people. So the probability of being both married and defaulting in this sample is 79 out of 300. So we would say that you have a 79 out of 300 chance of selecting someone from our sample at random and having them be both married and defaulting. 0.263. Married and non-defaulting would be this box, the intersection between married and no default divided by the total number of people in the population. So for single and default, it would be the box representing both single and default, dividing by the total number of people in our sample. And for single and non-default, we can take a look at that intersection of people who are both single and are current, who have not defaulted, 116 out of 300 people. We can express these just in terms of numbers, and then we'll explain them kind of as percents really quickly. 26.3% of this sample is married and has defaulted. 21.3% of the sample is married but has not defaulted. 13.7% of the sample is single and has defaulted. And 38.7% is single and has not defaulted. Let me give you those formulas. And so now let's look at one more thing. This is our joint probabilities. The last thing I want to look at is conditional probabilities. If we know someone's married, what's the probability that they defaulted? If we know someone's single, what's the probability that they defaulted? So for these conditional probabilities, how we're going to think about it is, given this subsample of married people, what percentage of that subsample defaulted? And how we're going to write that is the probability that you defaulted given that you're married. And then we'll take a look at the probability that you didn't default. That's that default prime given that you're married. We'll do the same thing for single. Probability that you defaulted given that you're single, and the probability of default prime of being current on your mortgage given that you're single. So for both of these things, we're going to be taking these as a row. So given that we're married, it means we're only dealing with people in this row. So what's the probability of default for people in that row? If 79 married people defaulted, that's 79 out of 143 people. That's about 55.2%, which means that if we reduced our sample only to married people, the probability that the person only of married people, probably the sample of married people that you'd pick out, that individual would have a 55.2% chance of having defaulted. If we look at people who are married who didn't default, that probability is going to be those no's, people who are current, out of that 143. So here we're only looking at married people, right? That's a conditional probability. The probability of defaulting or not defaulting given that they're married. We can do the same thing for single people. The probability of defaulting given that they're single is going to be 41 out of 157. If we reduce our sample only to single people, there's a 26.1% chance that a person pulled at random will have defaulted. And to see about current, that would be 116, out of 157. All right, those are our, I'll copy and paste some formulas. And now you can see these as proportions or as probabilities. So that's what a conditional probability is. They make a lot of sense if you've got empirical data. The thing is that where probabilities become useful is not when you have historical data, but when you're trying to predict what's likely to happen in the future when the outcome is uncertain. And so when we don't have this data, we have to root our mind in the fact that this actually makes quite a bit of intuitive sense. But we're going to have to rely on a couple of rules. We're going to have to rely on what's known as the multiplication rule, and that can be written in two ways. The multiplication rule allows us to have two of these three probabilities, and we can solve for the other one. So I phrased the multiplication rule in two ways for you. The first allows us to calculate a conditional probability if we have a joint probability and a basic probability. Likewise, we can calculate a joint probability if we have the conditional probability and the basic probability of whether or not someone's married or single. So let's do that. And I'm going to here call this proving the formulas, or formula proof. I don't know, you can call it whatever you want. Typically, you won't be given an underlying table of counts. You'll be giving probabilities, and you'll be asked to use probabilities, a joint probability and a regular probability, to calculate a conditional probability. So let's just take a couple. Let's calculate the probability of default given that someone's married. Let's calculate the probability of default that someone's single using not the table of underlying counts, but instead, let's assume that what we have is only joint probabilities and regular probabilities. So to calculate the probability of default that given somebody's married, the formula is just the the joint probability that someone is both defaulted and married divided by the probability that someone's married. So we can calculate that here by taking the joint probability that someone has defaulted and they're married, which, take a minute and just note that the title that I use, or the heading in row 14, truly is the same as that denominator. It doesn't matter the order of the D and the M. And I'm using the and because I don't have the upside down U. And I'm going to divide just by the probability that somebody's married. And that gives me the same number here as here. We can do the same thing for the conditional probability. What's the probability that someone's going to default given that they're single? We take the same thing, the joint probability of default and being single, 13, and we divide it by the probability of being single. And we can confirm here that the probability of default being single matches. Let's do it again. Let's calculate a couple of joint probabilities. Let's calculate something different. Let's calculate the probability of being married and not defaulting. Let's calculate that joint probability. And let's calculate the joint probability of being single and not defaulting. And we will do that using this bottom piece of the formula. It's going to be equal to the conditional probability of being married and current on your loan multiplied by the probability of being married. And if you think about this, it's basically just saying the probability that you default given that you're married multiplied by the probability that you're married. Or in this case, the probability that you don't default given that you're married multiplied by the probability that you're married. So let's take that here. We're going to go to the probability of default prime given that you're married multiplied by the probability that you're married. 21.33. Right, and that matches here. And the same thing for being single. Probability of being current on your mortgage given that you're single multiplied by the probability that you're single in the first place. 0.387. I realize that's kind of a lot. But what I want you to get out of this is to see that probabilities, the underlying probabilities, are based on a proportion of individuals or occurrences in a data that meet certain criteria. We're not always going to have that. But if this part makes sense, which hopefully it does, then it's only a small step to realizing that we can use the probabilities to solve for one another. So let me just copy and paste some formulas. There you go. I'll leave that up for a second. Happy calculating, and email me if you have any questions. All right. Have a good one.